Okay, we got a little bit change on the plan for the lectures. So I know that last time we talked about inheritance, but for your interest about what's going to be covered in the lab tests, I want to insert this particular lecture on math models, but which I plan to cover kind of after the reading week, but now I just move it to the front. We'll come back to inheritance after I talk about this particular lecture. But for now, today, we're going to talk about math models, especially how you do things together. In a way, hopefully that will give you more thorough understanding, given that you got working knowledge already for the math model from the labs. So for today, and possibly about the first 30 minutes of Wednesday, we do math models, okay? Especially why you're doing it. There's a design rationale behind that. And then we do some nice case study, which the other section actually did. So I think we better cover that, so we are equally prepared for both sessions. And as for the lab test one, we'll give you more precise guidance maybe on Friday. Okay, I'm still discussing with Jonathan about what should be covered in the lab test, but at least what's going to be covered in the math models, it will be covered in the lab test. Okay, that's guaranteed. Okay, so let's just start this brand new lecture over here about math models. Okay, at least we'll try to get some simple example done today, and then I'll give you some case study problem to think about, and then we'll solve the case study together on Wednesday. Okay, so we got 2 examples for the math models. Okay. So now, why are we doing complete contracts, right? As we talk about when we use across and also deep twin, you know, the O keyword. We talk about how you can write complete contract, especially post condition, okay? Let's just review very quickly just in one slide what we covered previously. So complete contracts, the lecture we talk about, especially for post condition, you want to make sure you address for every attribute how it has changed or unchanged, you know, after executing the body of the feature, okay? So it's going to be a relation between pre-state and post-state. So that's a principle we want to always remember. And then the use of the O keyword is really important, right? Okay. But for now, I assume you are comfortable with the lecture. So we're simply going to use deep twin for the O keyword for the completeness reason. Okay. And then for composite structure, which we'll talk about today, especially array, linked list, or tree, or multiple arrays, for example, right? That's something you are expected to solve in the lab test. If I give you multiple data structure as the implementation, how do you specify a post condition as complete as possible, right? The answer is, ultimately, we want to use a math model, okay? Now we'll get there. And then, okay, you want to say what's really changed, maybe one particular spot in the tree or an array, and the rest of the structure shouldn't change. For that part, we'll use the across syntax, right? That's something we'll also review today. And we'll do some exercise together. Since the slides is not up just yet, don't check the previous year, okay? I fixed some typo there, actually, just before I came here today. Okay, so now let's talk about, you know, let's have a very, very simple example just to illustrate the points, okay? And then I'll give you some case study to think about before Wednesday. We'll talk about a last in, first out stack. It turns out that even simple example like this will be very valuable to use a math model. But again, as usual, before we really appreciate, for us to appreciate why math model can be beneficial, let's try without a math model, okay? Let's see how things will work. This is kind of the plan, okay? How would you implement a last in, first out stack? You have at least 3 implementations, you know, based on what you learned, maybe in 2030 or possibly 2011 for sure. Okay, let's just do a quick summary, and then we'll get into writing contracts, right? So the implementation itself is trivial; it's not the points. It's really about how you can write contracts accordingly in a way that your design is extensible and maintainable. Okay, so let's talk about 3 different strategies. Okay, so now let's say we can either use an array or to use a linked list. Okay. Let's say, how do we implement the counts feature for the stack? So basically, on the leftmost column, we talk about features for the stack, not really for array or linked list, right? The array and linked list, they got different features that are supported. How do you implement a count? Well, that one is trivial. Just say implementation account. Okay. So now the imp over here can either be an array or it can be a linked list. But now, in the case of the linked list, let's have 2 alternatives. Either you say the beginning of the list is the top of the stack, or the end of the list is the top of the stack, right? You got 2 possible strategies. Maybe the way you write the contracts accordingly would be different. Okay, let's see. Well, we'll talk about contract. That's the main point. So we got top over here. Let's say for now, strategy number 1, we simply treat the end of the array as the top of the stack. We simply keep inserting to the end of the array. Okay? And for the linked list, let's say we got two strategies. Strategy number 2, we simply say the first of the list, the front of the list is actually the top of the stack. So what does that mean? Every time when you want to push into the stack, you're basically inserting to the front, right? Keep inserting to the list, prepend. And then the third one is going to be similar to the array implementation. It's just that we say the last element in the list is just going to be the top of the stack. Are we okay so far? Okay, all we have to understand is we got 3 different implementation strategies. And remember, according to information hiding, since we can constantly change from strategy 1 to strategy 2 or to another, this kind of a change should not bother the clients, which means we should really hide this kind of secret from the clients, right? That's what we learned. We'll see. Okay, and what about the push? Well, accordingly, for the first strategy, simply force the element to the end of the array, okay? And also, you can put to the front of the list, or you can extend the list to the end. I assume you're okay with these features, right? By the way, in lab test 1, you are not only assuming you're comfortable with math models, but also you should be comfortable with a library structure like a list and array. Okay, that's why this lecture can be a nice review for you. Yes. Put front, good, I like that. Yes, that should be put front, sorry. F-R-O-N-T, I'll fix that, good. And also, what about pop? Since we're gonna, pop will simply just remove the last element in the array, so I would say remove the tail. You can check the array API. Or you can simply go to the start of the list and then remove it, right? Okay, so now we are okay. Any questions so far about the 3 strategies? They're easy. The contract will be the interesting bit for this lecture, okay? Good. So now, yes. So for, well, okay, about a lab test, basically you will be expected to be comfortable with Eiffel Studio. So let's say if you're not so sure which feature you can call on the array or on the linked list, of course you can just search within Eiffel Studio, that's fine. Yeah, that's absolutely fine. You don't need to memorize what's available in the library. You should know, just have a rough picture what classes you can use, okay? But most likely just linked list and array in the lab test, most likely, or a combination of the both, okay? But we'll get to there. Okay, so now, given that all the strategies are meant to implement the same abstract data type, which means a stack, all the 3, okay? We support count, top, push, and pop. Now the question is, are we going to have the same contracts for the 3 versions? That's the question, before I get to, for example, let's say push. If you're to write the push feature for the stack, let's say, are we going to have the same post condition for push between, let's say, strategy number 1 and strategy number 2? Yes? No? Just roughly, why not? Yeah, somehow you gotta be careful with the indices, exactly. I'll let you work out the details for us, exactly, when we get to the slides. Yeah, that's good. Okay, at least you want to have an intuition. Because the implementation strategy is different, that means the way we draw the relation between the post state and the pre-state will be different. Okay? And now, one thing I want to remind you about, single choice principle, right? Single choice principle, anybody want to repeat to me what that means? Single choice principle? Anyone? Yes. Yeah, whenever you want to make a change to this design, there should be only a single place or at least a minimum number of places. Very good. Yes. Now, as I show you the 3 versions over there, think about whether it will conform to or violate single choice principle. Okay, that's kind of what you want to keep in mind. Okay, so no math model just yet. Not yet. We're trying to motivate you. Right? Okay, strategy number 1. We have in the array to implement a stack, and also the end of the array is the top. Okay? So now let's have a quick look. Okay? The implementation will simply declare that to be hidden from the user, simply export it to none. And then the make feature, simply make an empty stack. That's easy. And now for the push, we simply force the new element into the end. That's good. Now, contracts. Tell me something. How many post conditions do I need? How many? 1? It's okay. Okay, well, maybe asking you about a number is not really meaningful. You can combine them using conjunction, right? So now, just describe to me informally, what postcondition do you need? The size goes up, okay, but size is only about the size, right? It talks nothing about the contents. Yeah, you want to make sure not only that you're adding something, so the size will increase. One of them, yes. Okay, what about the contents?
Make sure that your new array is the same as your old array at the beginning plus the new element that you placed.
Yeah, when you say the new array is kind of equal to the old array plus something, right? That informally that works, but you wouldn't say array plus something, right? Yeah. What you're describing here is more like a math model concept and not really implementation. Okay, let's save it for that. Any thoughts for you? Easy one. Okay, tell me the post condition that's going to address what's being changed by push.
Well, first of all, is the size, and second of all,
Into where?
Into
the actual array? Where? Where into the array? To the end of the array, right? Okay, good. So that one's good. Implementation, position count. Let's assume Eiffel convention, indices start with 1. Okay, until count. Okay, so the last position in the array is going to be the same as whatever new element we want to push into the stack. Okay, let me just move my mouse here. Okay, G is exactly what we want to push into. So far, so good. What about a second post condition? Let's do a warm-up only. In the case strategy number 1, it's quite easy. Okay, anybody? Let me give a little bit hints. Okay, not here. Basically, we talk about strategy number 1. Okay, strategy number 1. And then let's say conceptually, right? Let's say what I really want. Let's say I already have a stack that has Alan and Mark. That means I should have an array that's being set up like this. Okay, index 1, index 2, and then Alan should be the first one. And every time I want to push, I simply push to the end, Alan and Mark. Okay, good. So that's kind of the what I start with. Let's say I want to do a push. And then when I do push, let's say Tom. Okay, conceptually, what I should have is something like this. I should have a new array. You can think about new array being a deep twin, right? Or the old array being a deep twin, actually. So now what we should have is something like this. So 1, 2, and 3. And then this part here should just be the same. Whereas the new one should be added to the end of the array, right? Something like that, right? You can think about this is the old guy, this is the new guy. So now how do I specify the contract saying this part is basically the same as the old part over here, entire thing. What we just said was this part here is really being added, right? That's what we just said. So now how do we say this part here? Okay, this one is so easy, but why don't you just say it verbally, and then we'll do the second one, a little bit more details. Yes, you first, yeah.
For all across.
Yeah. From where to where?
From our older array. Oh, do the new array from 1 to count minus
okay.
1, and make sure that that is the same as our new array.
Mm-hmm. Okay, I'm just trying to be picky on what you say. You're saying that for the old array from 1 until count minus 1, that means you're only talking about this one. Should be the entire thing, right? Okay. What about we say that for the new array, we're going to do from 1 until count minus 1. And then every element there in the corresponding position should be the same as the old one, right? Okay, here should be the same as that. Okay, conceptually that's easy. The first one is really easy. I just want to make sure we are on the same page. This is a warm-up. Okay, that's what we'll get. Okay, are we okay with this? Basically, you want to say from 1 until count minus 1. Question here for you. What if rather than saying count minus 1, I say count? Should I get any counter violation?
Yes.
I should, right? Right? Because if I only do count over here, this will actually happen if the supplier is actually a good supplier. which means I simply go from 1 until count, which can be 3. And I use 3 to reference back to the old array, which doesn't exist for index 3. Good? Good, very good. That one's easy. And now we do something similar for pop. Okay, I'll show you quickly. And then for pop, we can say, well, we simply say count should be O count minus 1. Good. And what about over here? Something similar. You can think about pop is more like a symmetric specification, you know, as opposed to push. Yes?
Would it be equivalent to taking the subarray and comparing?
Yes, you may do subarray, yes. But remember, since you got a cross, which corresponds quite nicely to universal quantification, why not just using a cross?
Would you need to use a cross, or would you?
I would say it would be, to me, it seems to be the simplest way to do it. Would be using the across. But if you want to use a subarray, that's also fine. Yes, you can give it a try. Yes. All right, that's good. What about the pop? Now the pop is going to be something similar, right? So now let's see if you might be convinced. We simply again go over 1 to count. Okay. And then since we are reducing the elements, right? So that means the new array is actually should be one size smaller than the old one, right? So now when we go from 1 to count, it should be okay. Okay, think about the logic a little bit, okay? Because the interesting one is really for the second strategy, where the front of the list is actually the top. That's the interesting bit, okay? But we'll definitely talk about that one a little bit more. Any question about strategy number 1? You can expect strategy number 3, the contract would be very similar to this guy over here, because strategy number 3, you simply say the back of the list is simply the top. Yes?
It's just not kept last name, though. What if you actually remove it? Like the count change?
You're saying which one? You're saying the push or pop?
Pop.
Pop?
What if it modifies count, but then it just swaps the last element?
Yeah, that's true. Yeah, so now it depends on whether count is actually the attributes or the query. We can say, let's say count is simply a query, which will simply return the size of the implementation, making it a bit easier. You're right. What Ken just mentioned is a very good point. Let's say in the case where count is actually in attributes, that means you can easily just decrement a count without doing anything. Absolutely right. But let's say we assume the count over here is simply just a query on the size of the implementation. Let's say. Good. Very good. Yeah. Okay. Let's talk about the second version, strategy number 2. Okay, so now we talk about another lethal stack over here. So this, again, you can see the implementation here with simply a linked list, right? And now, make feature is not very exciting. You simply create an empty stack. And now for push, okay? Now this is where I need your help, okay? Now think about it. So now you can see the implementation here. We simply put to the front in order to do the push, right? Now, similarly to the case where for strategy number 1, we need 2 post conditions. The first one is easy. Why don't we do the first one quickly? What will be changed? Used to be implementation at position count. Should it be the same? No, right? What should that be? First element, okay, good. We can say imp.first. We can say imp brackets 1. That'll also work. Okay. So far, so good. Now, I want somebody to tell me what the post condition should be using a cross. Actually, let's set up some ground, okay? Otherwise, there may be more than one way that you can write it, okay? Think about what strategy number 2 is, okay? So basically, we talk about strategy number 2, okay? And then let's say we talk about the same stack over here, and then again, we have Alan here, and we have Mark here, and then we're trying to push Tom. What would be the setup at the moment? It should be, let's draw kind of like a linked list, right? So this will be the first one, followed by another one. So now, because now the front should be the top. So that means I should have Alan over here and Mark being over here, right? Every time when I try to push, I simply insert to the front. Okay, so far so good. And now let's think about conceptually what's going to happen. And of course, for the linked list, the position is going to be 1 and 2. Okay, let's say you can definitely do that. So now let's think about if you want to do, let's say stack, you want to push, again, you want to push Tom conceptually. So that means Tom should now be the top of the stack, right? So now let's try the following, okay? Again, conceptually. You can think about this guy here is the old guy. And this guy here is a new guy after we try to say put front, right? And now the new guy should look something like this. It should be basically, what should be the first one here? Tom, okay? Make sure you understand that. Okay, Tom, followed by Mark, followed by Alan. And let's be more precise about the indices, right? It should be 0, oh sorry, not 0, 1 and 2 and 3. What we just said on the slides, we say imp.first should be G. Imp.first, which is worrying about this particular part. So we have already done with this part here, but the rest of the new array, the rest of the new list is not handled just yet. Anybody can help me on the across. Somehow, I want to say something like somehow. I want to say this guy here, the same as this guy here in the old. Similarly, this guy here, the same as this guy here in the old. But the problem is the indices are not quite the same. Not quite, but there's a pattern there. -1, I agree, that's good. But now, how do we write across accordingly? You might have to deal with this in the lab test. So let's practice that now. You may or may not. Yes. Maybe I'll let him try. Okay. Okay, let's try that. How about this? I will set you up over here. I can say across from what integer interval would you like? 1 until count. 2 until count, I agree. Okay, 2 until count as, what about we just say I? Okay, universal or existential? Oh, well, all means universal quantification, and some means existential. So which one would you like to use? All. Good. Okay, very good. Now, this part. Yes, go ahead. That's why. Yeah. Just help us out. Just tell me the Eiffel syntax. How about that? I will tell you if that compiles or not. Imp. Let's say imp. You mean the new version, right? Imp. At position what? I agree. Equal to, you mean the tilde here, right? Let's say, right? So you always do the object comparison. Yes. Deep twin, you mean which deep twin? Imp.deep twin? Deep twin? Mm-hmm. Should I put any brackets?
Yes.
And then, okay. Mm-hmm. That sounds reasonable to me. That's pretty good. Thank you. Of course, I think during the lab test, without my being so annoying, I think you'll be even faster, right? Any questions? Yes.
What if you start off an empty list?
What?
Push 1, but then the 2 is not going to be this.
Good question. When you say empty list, that's a very good question. You always start the collection with empty collection. Think about what's going to happen here. If you got empty collection over here, what's going to be the count? So the question really is empty collection. It's a very important question. Empty collection. When you got empty collection, that means count is simply 0. So now from 2 until 0, there's no such thing that can sit between 2 and 0. So that means it's simply equivalent to false. And we talk about, when the range for the universal quantification is false, it's simply the true automatically. Okay, that's okay. It's worth reviewing that. Yes?
Can a cross not go backwards? It cannot go from...
Yeah, I see what you mean. Yeah, you're basically asking, can I say across maybe from count down to 1 as I? That'll be convenient, wouldn't it? I'm sorry, no. Actually, I would like this to be extended to the Eiffel language, but no, I'm afraid no. Yeah. But you can, if you, let's say if you really want to go the reverse way, right? Well, that's easy. You can simply say, if you say across 1 until the count, right? And then as I, R, and N. Sorry about my writing. So now, let's say in the loop, you really want to say, rather than 1, 2, 3, 4, you want to say 4, 3, 2, 1, right? You can massage the expression a little bit, can you? Absolutely. Count minus, maybe I the item, something like that, right? You can definitely do that, yes. Okay, good. Then you know all kinds of programming trick. Yes? Yes, if the linked list is simply empty, the rest of the list part is simply just empty. So it will pass trivially, yes. Yeah, since we talk about universal quantification, if the range is simply just empty, false, it's just true automatically. Okay, something important to keep in mind. Okay, guys, any question about this? Yes? Yes, you may. Yes, you may. However, in this case, no, because lower and upper is only for array. Be careful, okay? Guys, it's really important for you to keep this in mind because don't ask me during the lab test why. When you say list.lower, it simply gives you compilation error. Don't ask me why during the lab test. I'm not going to tell you, okay? Huh? First and last, simply the element. When you say list.first, it's simply equivalent to list at position 1. Okay? Good. Anyway, you got to review list and array before the lab test. Okay, we okay with this? Good. So now if we go back there, that's exactly what you will see. Very good. So now, pop will be completely symmetric. Okay, I'm not going to bother you too much with that. I'll show you the answer and then you can verify for me. Okay? Change will be, again, we can say the account should be decremented. And also, it will be something like this. Okay, basically now, the new array is actually shorter. One should be one element shorter. So that's why we can go from 1 to count, and then we simply say from until 1 until count is simply just going to be the same, right? But don't forget, you want to take into account the offset of 1. Okay, good. Any questions about this? We're almost there to make a conclusion. Well, mini conclusion, not conclusion. Okay, good. That's about strategy number 2. And one thing to note, the way we write a post condition, even though conceptually it's really about comparing the old and the new array, but the way we write it is completely different. Agree? Good. Let me just show you very quickly a third version, and then we'll talk about something. Okay? Talk about design. Now, the third version over here, we're still going to use a linked list, and then the strategy number 3, rather than the front of the list being the top, now the end of the list is the top, which means it's basically the same as strategy number 1 using the array, right? And, okay, so you can see that for the push, we can get almost the same contract, almost the same, okay? The only difference is now the way we refer to the last element, we say imp the last. Of course, you could have said imp a position count, that also works. But, just show you some variety. And if you do the pop, it's also going to be the same as how you did it for strategy number 1. So now we have seen 3 strategies. Okay. Oh yeah, exactly. So you may, I agree with you. You may want a precondition, which I didn't really emphasize so much. For a good design, you may want to say for the pop, you have a precondition saying maybe imp the count is strictly larger than 0. You may want that, yes. But the reason I didn't show it, I don't have space over here. So I just want to show you the post condition only. That's why. Yeah, you definitely should need a precondition for this case. Yes. Okay, good. So now, let's now talk about design, right? Basically, what we have got was basically the 3 versions over here, right? You can see strategy number 1, strategy number 2, and strategy number 3, right? You have seen the details already. Now, question for you, is it a really good design? Meaning that basically, even though the imp being either array or list is exported to none, that's true. Which means nobody can actually get access to how you do the implementation, that's true. However, in all the cases, somehow we expose the details about the imp over here. For example, you can see in strategy number 1, we simply have imp over here, and also we have an imp over here, right? In strategy number 2, similarly, we also got imp over here, we also got old imp over here, similar, right? So now, is this exposure in the contract level to the clients about what your imp is really a good idea? Should not be a good idea, right? But now, we want to justify why not. And of course, usually when you want to justify if a design is good or not, one way to do it is to say, oh, this violates a certain well-known design principle. Okay? So now, which design principle do we want to say? Well, I would say information hiding, that's true, but you gotta be careful. Because when you say information hiding, I can tell you, okay, the imp, for example, is exported to none, which means nobody can actually call this particular imp from outside, right? So if you simply say information hiding, it's not convincing enough. What you should really phrase instead is to say information hiding was not really well conformed simply because you didn't really hide the implementation from the contract view. Okay? Even though people cannot really call the particular imp, but people can still see it from the contract view. That's one thing. But let's go a little bit further. What about single choice principle? Single choice principle. Anyone want to, does it satisfy or not satisfy single choice principle? Yes. That's true. You're talking about the labs. Yes, I agree. Yes, that's something you eventually will get into. Yes, absolutely. So, for example, let's say this. Let's say we are doing the following change. Let's say currently we are using strategy number 1, let's say. And then we decide to go from strategy number 1 to strategy number 2, right? We want to go from here to here. It's a change on the secrets. However, it's not only that we have to change just the implementation part accordingly. That would be what I call the minimum number of places you change, right? You want to change the implementation itself, right? This part over here. Not only that, what's going to be very bad is you have to really modify the way you write a contract. For example, you can see in strategy number 1, here you say I.item. On the other hand, for strategy number 2, you say I.item minus 1. And also I.item plus 1 versus I.item. So these are changes on the client's view on the contracts. So that means you got to modify not only the implementation, but also the contracts. So that violates single choice principle. Okay, are we good? Okay, so now I'll just say not only implementation, but also contracts. We must modify accordingly. So this means it violates the single choice principle. Okay? Now, are we okay with the problem? Okay? So that means in the lab test, when you try to do your implementation, you want to choose as efficient data structure as you can. But for the contracts, you want to really choose something that can be reused when you go from one implementation strategy to another. So now let's go to the mini conclusion. So what should we use? Math models. Okay? That's something we didn't really tell you the rationale behind for lab 1, 2, and 3. Somehow, it's a different approach. Rather than saying we teach you the lecture first and let you practice in a single lab, we kind of do the reverse order this semester. We let you simply without understanding exactly why you're doing math model first, and then you have some working knowledge programmatically, and now we talk about the rationale. We'll see how that goes. We can adjust that a little bit next semester. Okay, point number 1, do we understand very well? If you simply use the imp directly on the post condition, it's going to violate single choice principle, number 1. Okay? If we agree, let's see how the math model can actually help us. Okay? Conceptually, it works like this. Conceptually. Let me just sketch the idea very quickly. Conceptually. You can think about, let's say this. Okay, it's too big over here. Good. Let's say if you have some class, or just C, just conceptually, okay? We have a class over here, and then you have some implementation, of course, is exported to none over here, which can be certain type, which is a secret to the supplier, which means you may want to go from one question mark to another, right? So now, if you think about, let's say, feature 1 and feature 2, right? So now, what we want to achieve is something like this. We want to say ensure, let's only talk about postcondition. The precondition is something similar, okay? Ensure over here. So the not good solution is you simply expose imp over here. That simply means whenever you change from imp to another question mark, you want to change that to another way of writing the same contracts, right? That's what we said is not good, conceptually. So now, what we want to do is like this. Can I just copy this guy here, and then just go to the next one? Okay, so now let's talk about what does it really mean when you have a math model. It goes like this. So rather than having this, what you have to do is to define the so-called abstraction function. I'll explain a little bit more when we get to the math model for a stack. What we want to do is we want to have maybe a model over here, which is going to be certain type. Any class you can choose from the math models library. For the lab test, you're expected to know sequence, which you already work with, and also function, and also relation. I'll give you a little bit background about relation today if we have time. If not, then Wednesday. Okay? So now the model over here is going to be basically just some type from the math models library. And then here comes the critical thing. Okay? So now, depending on what the implementation is, this part over here, the implementation for the abstraction function, the model, is going to change accordingly. That's the only place you have to change. Which means, if today I try to change from the blue one into another pink one, another implementation, let's say going from hash table into AVL tree, for example, right? The model itself doesn't have to be modified per se. Only the implementation part has to be modified. In your lab number 1 and 2, the way you implement the abstraction function is trivial. You simply say model is assigned to implementation, right? You might be wondering about how useful can it be. I can tell you it's not useful, right? It's just to make it easier for you for lab 1 and 2. Yeah, the same. They should not be the same. They should not be. Good. So now let's say, as we are going to learn about the case study for birthday book eventually, what can be a good model for? Let's say we learn about dictionary, kind of an abstract data type, right? So what can be a nice mathematical model for dictionary? Should it be a relation or function? Why should it not be a relation? That's a design decision you have to make. Think about it. I'll revisit that point in a little bit later. Okay? Oh, you wanna? Yeah.
Like C should be related to only one value.
Yeah, relation simply means each domain value may be associated with multiple range values. But you want to say if you give a key, it should not be giving you more than one values, right? That's a very quick justification. Good. So now, conceptually, you can think about when you change from one implementation to another, the only place you have to modify is how you convert from the implementation to the model. Like how you go from AVL tree into a function, how you go from a hash table into a function. That's the only part you have to change. That's a single place, conceptually. Now, what about contracts? That means for all the contracts you gotta write, you don't write them in terms of the implementation anymore. You only write them as model, the orange part. Now, I'll give you one scenario, just as a quick recap, and then we'll talk about example. When I move from the blue into the pink, okay? Let's say I change from hash table into AVL tree, okay? The only place I have to change is to see how to convert from, let's say, how to convert. Used to be, I convert from hash table, convert from the hash table into a function. Now I want to define how to convert from AVL tree into a function instead. That's the only place I have to change. But anything else, when I write the contracts, I wrote them in terms of the model, the function. As soon as I change the definition for the abstraction function, everything else will just be changed accordingly. without modifying anything else. That's why it's single choice principle. Guys, that's a very important concept for you in order to succeed in lab test. Okay? Questions? Okay, good. So let's talk about how we can apply this concept over here to the stack first. And then I'll give you a little bit exercise before Wednesday, and then we'll solve it together. Okay, that's kind of the plan. So now let's go back to over here. Okay, so now, now information hiding, and then also single choice principle. Okay, we talked all about these, right? It's already set. Okay, single choice principle, very important. Okay, math models. How do we create math model? Basically, we want to create a math models that can be used for all the 3 different strategies of the stack. Whenever you go from one strategy to another, we don't modify the contracts themselves. We only modify how do you convert from this particular strategy of the implementation to the model. That's all we do. Okay, let's see exactly what I mean. Okay, so now let's see the next one to see. I want to show you a little bit of code. So for the math models, this is also something you have picked up already from the previous lab. I'll mention that very quickly. For every math model class, let's say sequence, let's take a sequence for example. Also the same applies to relation and function. For every math model class, you got 2 kinds of feature you can call, either a query or a command. Query simply means you're going to return something so you can use in the contracts to create some Boolean expression. If it's a command, that means it doesn't return anything. So you don't really want to use the commands in the post condition, right? That's something we said, okay? So now I want to show you the code very quickly, okay? And then we'll talk about how this can be applied to the stack example. Let's talk about, okay, so again, over here, I'm talking about abstraction function. I want to give you a little bit insight about why this is called abstraction function, okay? Abstraction function in the sense that we don't really want you to think at the level of the code. I don't want you to think in terms of the hash table, AVL tree, or array when you write the contracts. When you write a contract, you want to think in terms of mathematics, discrete mathematics that you learned in 1019 or 1090. Okay? So now, thinking conceptually, that's what we're doing here. Strategy number 1, we are using array. Strategy number 2, we are using linked list. Okay, and then where the front is the top of the stack. In strategy number 3, we also got another linked list implementation where the end of the list is the top of the stack, right? So all these strategies are at the level of the code. They are not very high level for you to think about and reuse the concept. So what we want to do is we want to create an abstraction out of them, meaning that the abstraction can be uniform among the 3. So what we try to do is we want to say all of them can be abstracted as a sequence over here. So now this can be abstracted into a sequence, and this can also be abstracted into. Oh, by the way, this is not inheritance. Okay, don't get confused. I'm just trying to show you the idea. Okay, you're trying to promote from array into sequence, and also from linked list into sequence, and from another strategy for linked list into sequence. That's what we're doing. It's not inheritance. Okay, just let me emphasize that. So now let's see how we can. So there are 2 parts of the math model you will have to do for the lab test or just for your knowledge. First of all, let's say we talk about a stack, and we talk about, let's say, just strategy number 1. Okay, so strategy number 3. Okay, so that's strategy number 3. Just make it easy. So we simply have a linked list over here. Okay. And then, so now the model over here is the abstraction function, okay? Pretty much like how you did it. Let's say simply just a sequence. So now this is the part you have to modify when you go from one strategy to another. That's the only part you have to modify, okay? So now in this case, how do we do that? Well, we pretty much, let's say we have the convention here. So when we talk about the sequence model for the stack, okay, the sequence model for the stack, we simply say the end of the sequence is the top. Okay, this is what we decide from the user's point of view. Whenever the users want to look at a contract for the mathematical sequence, they can always assume, regardless of which strategy is being implemented under the hood, always the end of the sequence is the top. of the stack. So conceptually, you always insert to the end of the mathematical sequence for the stack, always. Okay, let's do this guy here, and then for strategy number 1, we'll talk about how you can do for strategy number 2. Okay, so now it's very conceivable here. You simply create something like that. Okay, create a sequence to be empty to begin with. You simply go across the implementation. In this case, strategy number 3. It should just be in the same order of the sequence, right? Should be the same. So you simply go across the implementation and then keep appending, like that. How does it look like? Let's have a look right away. It looks like something like this. So here we got different strategy over here. Okay, that should be TEGY. Okay. So now let's see exactly what's gonna be like. So now over here we talk about strategy number 3. So now let's talk about strategy number 3 over here. Okay, strategy number 3, where at the implementation level we know that the end of the list should be the top. Okay, so now how do we create a mathematical sequence accordingly? Well, easy. You simply conceptually, you simply create an empty sequence to begin with, the model, right? That means model initially is simply just going to point to some empty sequence to begin with. And then you will go across the implementation one by one and then simply keep appending to it, right? You simply append the first one and then you get Tom. And then append the second one, you get Mark. And then append the third one, you get Alan. Very easy. You don't really see the value just yet. We only see the value when we get to defining the abstraction function for the strategy number 2. Then you will see the value. Okay? Now, I have an exercise for you. Okay? Let's say this. We talk about the class for level stack. And then over here we have, let's say, of course, don't worry about the generics here. I'm just sketching the idea. So now for strategy number 2, it is the linked list of some G over here. And then we talk about strategy number 2, which means the front of the list is the top of the stack, right? Now the question for you, how would you build the model for the level stack in this case? In a way that is going to give the user a consistent view of the stack without them worrying about whether you're using strategy number 3 or strategy number 2. Okay? That's the key thing. Okay? The way we did it for strategy number 3 was here. Okay? We simply say create some empty sequence. I can do that too. I can say creates result dot make empty. Now, can I simply use the same line over here to say across from implementation and then simply append one by one? Let's see if I do that, okay? For those of you who are still not very following. If I simply say across, I'm talking about strategy number 2, okay? I'm talking about number 2, okay? Just make sure you don't lose track. Across the implementation as cursor, and then I simply do exactly how I did it for strategy number 3, right? Remember they treat the top differently, right? Okay? So now over here, I simply say result dot append. And then I will simply say imp dot item. Will this work? Okay, if you really get lost, now is the time to wake up and ask me questions. So let me recap what we have got so far. Okay? What I just showed to you was this particular implementation for the abstraction function. It was implemented this way under 2 assumptions over here. Number 1, we are dealing with strategy number 3, where the end of the array, the end of the list is the top of the stack. Number 2, for the models, from the model's point of view, for the user always think the end of the sequence is the top of the stack. And this happened just to be identical to the implementation under the hood. So that's why we can simply keep appending. So now my question is, if I move on to strategy number 2, where the front of the list is actually the stack, can I reuse this model implementation here? Okay, good. Intuitively, you cannot, right? But how wrong can it go to?
Well, it's faster reverse.
Reverse, exactly. Let's see exactly how that's happened, and then we're going to fix it. Good, okay. Let's say I simply just try this. So I'm going to go across the implementation, which is strategy number 2 here. So now I'm going to go across over here. So ln, so initially result is simply, the model is simply just empty, right? And then I'm going to do the first one, append the first one, which is ln. And then I'm going to append the second one, which is mark. And then append the third one, which is Tom. So now what's the problem over here? You can see from the model, design model's point of view, you can see the user, even though it's the same stack, the same. However, strategy number 1, give me this model here. Strategy number 2, give me a reverse way of doing things, so the user will be confused. But everything still compiles. It's a logical error. So don't be too surprised if we put this in the exam and ask you why. It's not good, right? Okay. Guys, are we okay? So now, so far, you should really understand why this particular way of implementing the abstraction function for strategy number 2 is not correct, okay? Next question is, how do we fix it?
You do it across one account, and you resolve append count plus 1.
Yes, absolutely. You can play with the indices a bit. But I tell you what, let me save you some time. There's a feature called prepend. Yeah, there's a feature in, there's a feature in the sequence. Well, that's why you got to check, right? Yeah, in the model. So if you look up the, let me just highlight it. If you look up the feature supported in sequence, there's a pen, there's a prepend. Okay, you can just use it. Yeah, absolutely what you said before, you can definitely do that. No problem. But I would say under the pressure during the lab test, you may not want to try that. Just use prepend, right? Okay, basically prepend. Okay, if I change that to prepend, what's going to happen here? Well, I'm still going to go across the imp in this particular order over here, but now, when I try to really construct the model, it goes like this. Okay, let me just write it quickly. It goes like this. The first one is going to be, oh, you know what? I better draw it from here. Initially, model is simply empty, right? Initially, model is simply just empty. The first one is going to be Alan, prepended to Alan. And now the second one is going to be Mark. Now, rather than appending, I'm going to prepending, right? So now, prepend, Mark, over here. And the third one is going to be Tom, and also prepended to whatever sequence I've got. Okay? So now, if you look at the new model here, after we fix the abstraction function, this is consistent with this. Okay? It's a very important lesson for you to learn. Whenever you change the implementation, you want to make sure you define the abstraction function accordingly, okay? In a way that's consistent with. Yes, that's exactly, yes, that's right. So remember, we are making the assumption that the user simply say, yeah, the end of the sequence is simply the top. Yes, we are making that assumption. Of course, if I change that assumption, you're going to change things, right?
Let's say we change that assumption for strategy 2 to be like the beginning, then that further will work.
Yeah, but that's not a complicated matter. So I'm just saying, you will always be given how should the model be interpreted first. From there, you design everything else accordingly. Okay? Okay, guys, any questions? That's about how you can implement the abstraction function, and that's where the single choice occurs. Whenever you want to go from one strategy of implementing to another, you only change the way you implement the abstraction function, the model. Okay? Now, second part of the story. Assuming that you have implemented your math models, let me just go there and then show you what I want to show you. Second part of the story. Once we have implemented this particular map model correctly, among the strategies, the next question is, how do we use the model in all the contracts for the rest of the features? Okay? So now I'll give you one example here. I'll show it to you first, and then I'm going to show you exactly how it works. Once you understand this, you are basically conceptually almost prepared for lab test, almost. Okay? So now let's look at that. So now again, let's assume that we already got this sequence for the model implemented. So now we're going to look at, let's say, push, right? If I have the push feature over here, remember the model is a mathematical sequence where we make the assumption that the end of the sequence is the top, right? And now without visualizing too much, which I will do in a moment, can you just look at how the insured looks like? Look at that. It's quite a, well, should not be too complicated, right? So even you already got some working knowledge from the previous labs. How many versions of model are we comparing? 2 versions, right? The new one and the first one, the second one. Another question for you, okay? It's really important. You may not have noticed that. If you think about it, I have model over here. I have model over here, okay? This guy here and this guy here. Are they attributes or are they something else? What are they? Huh? They are queries. They are result of the query. So you can think about every mention of the model in your post condition correspond to a separate call to the model query, okay? So now let me get a little bit more intuition and then we can go on to visualize it, okay? Remember we talked about the complete post condition, about how to use the O keyword, right? So now if you look at where the O keyword is placed, it's placed exactly over here, okay? And there's a bracket over here, right? So what does that mean? That means that will force IFO runtime to cache some value for you. What exactly will be cached? Just model? Model that deep twin, right? Okay, exactly what's going to happen is, I'm going to just mention that verbally and then I'll visualize that to you. This expression here will be cached in the pre-states. What does that mean? That means in the pre-states, we're going to call the model for the first time. And then whatever return value is, make a deep twin of it. Okay? And that's going to be guaranteed to be completely independent from however model that's going to be returned the second time up in the post states. Okay? We'll visualize it, don't worry. Okay, so this will be a call to the query. Okay, and then this will be a deep twin of the return value. And then this guy here will just be a later call to the same query. Okay, are we okay? Okay, now let's study this post condition in more details. Because the way you write the post condition for any model type is going to be very similar. Very similar. Okay? I would say almost all the time you got to say model.deep twin. Almost all the time. I cannot think of any case where you don't need a model.deep twin. Okay. Good. Let's do it. Okay, so now let's talk about this particular one. Okay. Let's assume we have strategy number 2. Okay, the more sophisticated one, right? So now we have strategy number 2 where the front of the list is the top of the stack. Okay. Okay, I'm going to draw everything from scratch to make sure you really understand. Okay. We got pre-states, and also we got a post-states as a result from push Jim. At the moment, we have basically Alan, Mark, and Tom, right? That's the stack we have. So you can think about, at the moment, we got Alan, and we got Mark, and we got Tom. That's kind of the stack we're talking about. Okay, that's how we start with. Let's only talk about let's talk about exactly how the post condition will be checked at the runtime. Okay, eventually we are not going to check the post condition using the implementation directly. We're going to use the model. But how exactly is it going to be done? Let's see. Okay, so now I want to first of all to highlight the part that will be cached. We know that there's an O keyword over here. As we said before, this is the part that is going to be cached. Deep twin. Now let's see exactly how things will work. Okay. Okay, so old model.deep twin. When you try to do model.deep twin, it's a little bit sophisticated. I will try to give you complete details over here. When you just do the model alone, there will be some sharing going on. As soon as they say model, once you get a result and say deep twin, everything will be independent. Okay, let's see exactly how. Okay, so now if I try to say model over here, first of all, let's simply just get the model. If I simply say model over here, okay, it's going to point to some sequence and then empty to begin with. Agree? Okay? So now, you know what? Let me use pink since the color over there is pink. Okay, the model is going to actually point to some empty sequence to begin with, and then as we said before, we're going to go across the implementation, and then we're going to use prepend. Right? Agree? Okay? So now let's see exactly how things will go. When I do the first one, okay, you know what? Let me just move this a bit because I'm going to do prepend. It's better to do it other way. Okay, you know what? So now the model is actually going to point to some empty sequence to begin with, right? So now, when I say something like this, when I say result.prepend im.item, right? I'm basically creating some aliasing over here, right? Because imp.item over here is talking about string, which is reference type. That's basically saying I'm going to prepend a slot for the sequence. And then that particular slot is going to point to the first elements of the implementation, like that. So there is aliasing going on over here. So now I'm talking about without a deep twin. Okay? What about the second iteration? The second iteration, I'm actually going to get mark over here, right? So that means I'm going to prepend another cell over here, and that one there is going to point to the second elements in the original list. Are we okay so far? So far we do have sharing, which is not good if we do any change beyond the first level. Okay? So now let's do another one. Let's say we do the third iteration, and then it's going to point to the third elements of the array. Sorry, the list over here. Are we okay so far? This is only the model part. This is only the part for model. This is why we want to do a deep twin. As soon as we say dot deep twin over here, it's going to create something that's completely independent, right? Okay, let me just use maybe blue over here. So when you say model.deep twin, so this is model here, model.deep twin. It's simply just going to point to a sequence over here, right? And then everything else will just be independent, which means it's going to point to Alan here, and also Mark over here, and also Tom over here. That's a sequence. Guys, are we okay with this? Oh, we have to prepend, right? Beg your pardon. What I meant to say, sorry about that. Let me just do it again. So now what I want to do over here is, I will simply do over here. So this is sequence over here, and I'll simply do the first element will just be Tom. So I'll just make a deep twin of Tom. And the second one is going to be Mark. So this is going to be Mark. And the third one is going to be Alan. So it's going to be Alan over here. So this is really what's being cached in the pre-states. Model.deep twin. But there are two steps that I want to just show you, right? But what eventually get cached is the independent structure over there, model.deep twin. So whatever changes you make on the element itself, even if you, let's say you try to append a character to Mark, append a star to Alan, it's not going to change the model.deep twin, all right? That's something we said before, right? We're just applying that in another context. Are we okay? So now, what else? So this is only the pre-states, which means the IFO is going to cache the value for us so that we can use it later in the post condition. So now let's say we want to execute the push. We haven't done the push yet, by the way. We haven't done that. We're going to push Jim. Okay? Now, what should we do? What we should do is we can simply do the following. If you want to push Jim, so that means I'm going to create, from the implementation point of view, I'm just going to create a new cell for the list. Okay? And the new cell is going to point to an Jim. Okay? And then Jim is going to be the new top. So it's going to point to the original list. And rather than top being here, now this will be the top. That's the change on the implementation side, which we know very well how to do it, right? What about the model part? Okay? So now we know already that this part of the post condition has been cached over here. Now, there's another occurrence of the model, which is over here. How do we compute this model here? Well, it's just a separate call to the model query, right? If you try to do that, it's simply just going to execute the same body of code over here to say result, which is the sequence.prepend. Just do it over again, right? Just another separate call. Okay, I'll do that quickly. So now, what will be the first one I get? Now in this case. So model over here, the new model is going to point to some initially empty sequence to begin with. Okay, again, I really meant to do it the other way. That'll be easier for me to draw. Model is pointing to some initially empty sequence over here. So now if I go across the implementation, so now the implementation has been modified already, right? So now what should be the first element to be pretend? Thank you. Something like that. Actually, to be more precise. Yeah, let me just draw it, otherwise you'll be confused. Okay, Jim first, and then it's going to be Alan, so you'll be prepended over here to Alan, and then prepended to Mark, and also prepended to Tom. Okay, that's the new sequence. So now, if you look at that, if you look at how the post condition will be evaluated, we're basically comparing the blue sequence over there versus the green sequence over there. That's what we are doing. And what we're trying to say here, we're saying that the blue one should be the green one appended with, and notice that this appended over here is a query. Okay? More precisely, this query is so-called immutable query. Okay, I'll just mention very briefly. Immutable query in the following sense. When I say whatever sequence it is, the green one over here, when I say appended, that means without modifying this particular context object being the sequence, I'm simply just going to create another sequence with the argument added. Return back to me another sequence. It's not mutable. It doesn't really modify or mutate the original object structure. Okay, that's why it's called immutable. Okay, so now what we're trying to say is, if I say old model.deepTwin, which is this guy over here, dot appended with G, and G in this case is simply just Jim. So what I'm doing over here is, notice what's going to happen here. So that means I'm going to append Jim over here to be the sequence over here. Okay, appended, right? So now I'm comparing this sequence now together with the blue sequence. They should be the same. Are they the same? Yes, they are, in the same order. Okay? Guys, are we okay? Yeah, I think I'm drawing better to compare with last semester, so I'm quite confident you got it. Maybe. Okay, please, any questions before I move on? I tell you what, this is kind of the simplest example I can try to explain how exactly things go on, at the design level, implementation level, and at the runtime. It's really important for you to see your implementation structure can be very, very different from the model structure, okay? Which we'll see for the birthday book when I talk about it. Are we okay with this? Good. If you're okay with that, then I'll move on to give you a little bit more visualization, a little bit more conceptual affirmation, and then we'll go on with other things. Okay, we talked about this already, and then that's the abstraction function you can go over. We also talk about everything. One thing to notice, once we implement the model, the abstraction function, now for all the strategies, if you compare the code over here, the way we write the post condition is going to be all in terms of the model. Okay, you can see for the make, we simply say model.count is equal to 0. For the push, we simply say, well, exactly what I just explained, right? And now notice one thing. This post condition over here is going to be the same for strategy number 1, the same for strategy number 2, also the same for strategy number 3, all the same. The only thing you have to change is the abstraction function implementation itself, okay? Which is here. That's the only place you have to change over here. Okay? And by the way, you can feel free to use make it from array. That's also a support feature in the math model. Okay, also for the pop, so now these two post conditions will just be the same throughout the three versions of the strategies. Okay, so now let me just show you one more diagram over here so to help you understand a little bit better. Okay, basically what we are creating conceptually is something like this. Okay, think it this way. The green one, let's think about the red one. Red one is basically what you have been doing up to 2011 when you do Java. Okay, you always think about implementation, always. Okay, so you think about implementation over here. You think about implementation over here. So if I do imp.force to the end of the array, what does that mean, right? You simply just consider only this part over here. Similarly, if I move on to strategy number 2, if I got the implementation being a linked list, in that case, for strategy number 2, I simply say I want to prove to the front of the list, right? The implementation is different. But now what we are trying to show you over here is when you want to present a contract to your clients, you want to make sure you don't really change the contract. Actually, contract should not be changed ever. Once it's given out, it should be the same always. How do we do that? You want to use some mathematical objects to capture the essence of your design using sequence, relation, or function. Okay, so that's why we're introducing this extra layer over here, the green one. Okay, so now basically this is what we're trying to do. We are saying that we're now thinking in terms of the model, which is a mathematical sequence. Okay, so when I try to do a push from one sequence to another, I can think about, I'm basically always thinking about, I'm doing something like this. I'm saying the old model appended with the one I want to push is just equal to the new model. The same interpretation for another strategy over here is just the same, completely identical. Just the same. So now what's the difference? What's single choice principle over here? That means if I go from strategy number 1 to strategy number 2, the only place I have to change as a supplier is as follows. I have to make sure when I go from array into the mathematical sequence, in the pre-states and the post-states, right? We got two separate calls to the model. And also in the strategy number 2, when I go from the list into the sequence and from here to here, I want to modify that accordingly. That's the only place we had to change. Okay? Okay, just another angle of summarizing what's going on over here. Okay, we got about 5 minutes. I think we have some time. I will spend about 2 minutes tell you how you can review the rest of the lecture, which will be some mathematical background, which I think is optional if you're comfortable with relation and function. If you're not, stuff are there for you to review. Okay? Let's have a quick look. Let's go on to this particular, okay, the diagram here. Okay, so yeah, exactly what I said. Don't worry, I'm not skipping any detail. Everything has been said already on the iPad. Okay, so now that's a summary slides for why we're using math models. So we want to make sure somehow information hiding. You don't want to expose the private attributes or secrets in the contracts because they're subject to change. Okay, so we have an abstraction using a mathematical model. So basically, arguably speaking, all the implementation structure you have to deal with realistically, a dictionary, tree, or whatever you want to deal with, they can be easily modeled using function, relation, or sequence. Okay, so that's a very powerful concept we are learning back in 1019 or 1090. Okay, so you can just read it over. Just talk about the process of converting from implementation to model. Okay, so now when you change the implementation, you only have to change, you don't have to change what the abstraction is. It's always a sequence, always the same interpretation. The end of the sequence is the top. However, you just have to change how from the current strategy of implementation to be converted into the model. Okay, that's the only place you have to change. Good. Now, starting from here, it's more like a math review, reviewing what a set is, what a relation is, and what a function is. Okay, I wouldn't trouble you with this detail right now. I would say go over the slides if you don't feel comfortable. I would suggest you do at least skim through them. Okay, anything you don't feel comfortable about it, speak to me. Okay, I kind of summarize all you need to know. Okay, The only thing I would like to do together with you very quickly is as follows. You know what, before I do this particular slide over here, which is just some example about domain restriction, domain subtraction, for those of you who are still struggling, I can give you a little bit quick review. But before I do that, let me present to you the exercise problem I want you to think about before Wednesday. Okay? That's going to be something, what you will be given something around the same level of difficulty in the lab test. Around. Okay? That's why I talk about stack first, so you can think about a more complicated problem. I'll get to here if I got time, or if not, then in the beginning of Wednesday. But you can definitely go over that too. I want to present to you the problem first, okay? For case study. Oh, you know what? Especially if you forget about what's really power set, it might be worth reviewing, right? It's kind of nice to know, okay? And also relation. Okay, so these are just math review that you can go over. What I want to go is exactly to the case study problem. Okay, I'm getting there. That's the example test I will go over with you. If not today, then definitely on Wednesday. So let's talk about some case study. So now, let's try to see how you will apply what you have learned up to now. How would you create a mathematical model in order to write contracts for a birthday book application? In fact, you might just realize yourself, the birthday book is just one example. It's really solving a much more general problem. We are really trying to solve the dictionary problem. We got unique key lookup, basically. Okay? Let's see. I'll present to you what the problem is. Oh, by the way, I might include a link. If you're interested about how to do a birthday book in Java, this is actually what I put for 2030. For those of you who did 2030 with me, we did a birthday book, remember? So now it's actually quite a nice continuation. You learn about how to implement that using loops, etc. in 2030. But now we see how to use mathematical model to write contracts for that. I'll include some link for you if you are interested, but it's not required. Let's see what a birthday book is. A birthday book simply stores a collection of entries. Each entry is simply just a pair. Person's name, just a string, and also their birthday. Okay, so it's not really generic. Okay, just a name and also birthday. And so now, no two entries stored in the book are allowed to have the same name. So that means we intend to use the name as a lookup key, right? Okay, no. And also the birthday book, the birthday, for simplicity, let's say only month and day. Let's not worry about the year, okay? And then initially the book might just be empty. Let's say we don't have any maximum capacity. Let's say we don't, okay? And then given the birthday book, what would you like to do, right? You may want to say the number of entries, that's easy, just a count. Or you may want to say add a new entry. So now this is interesting. Let's say I already got Jim's birthday in the book, in the birthday book. What if I try to add Jim again into the birthday book? What should be the behavior? Let's say we simply want to override Jim's birthday. Let's say Jim's birthday used to be February 12th. And now I want to modify his birthday to be February 13th. I can add Jim again just to the same book. Okay, something like that. Okay. And then we can remove the particular entry. Okay. And now this is the interesting bit. Okay. Let's say I want to know who will actually born on February 13th. I want to remind them. I want to remind myself so I can send some birthday greetings to them. Okay. The last operation is the most interesting bit. How would you write some contract for that? That's the interesting part. Okay. Given the birthday, basically given the birthday, how can you find all the people who got that particular birthday? Okay. Okay. Give me 1 more minute and then I'll be done. Okay, the birthday book. So now there are several decisions you have to make. You have to make some design decision. You also have to make some implementation decision. Okay, design decision. What should be the classes you need? Think about it. And should there be any client supplier? Should there be any inheritance? Think about it. Okay, and also what should be the mathematical model? Anyone? Okay, function. I'll discuss why it should be a function versus relation. We don't have time now. It can also be a sequence. It can be a sequence of pair. But it's not such a good model because sequence has order. Collection shouldn't be any order, right? Good. Okay, let me just say one more thing. Okay, give me 30 seconds, okay? Contracts and implementation decision. So now you can either choose two linear structure array like how you did in 2030. What should be the big O for that? Question for you. Linear, right? So now, if you want to use a search tree, assuming that's balanced. Log in, good. Okay, that's kind of the decision, right? Nothing to do with this course, but just as a reminder. Can it be even more efficient? Hash table, it can be constant, right? Assuming that there's not too much collision. All right? Okay, so now, of course, whatever you choose, you want to implement the abstraction function, the model accordingly. Okay, think about these two slides of problem we are having here. Think about it, and then we'll talk about the solution on Wednesday. Okay, see you.